Let's start. So, right, welcome to the Rubin Research Bytes. This is the AGN and Microlensing meeting, or sub-meeting, or breakout session. Chairs are myself, Franz Bauer, and Sophie Reed. Of course, we're starting 15 minutes late. We have a 30-minute agenda that we're going to repeat.
Oh dear.
And hello. Is that noisy? And right, so the idea is I'm going to give a brief introduction, and then we'll have 3-minute talks, 4 3-minute talks, and then we'll have followed by a question and answer session. If you want to post your questions in the chat here, or in ideally Slack, so that people can respond to them later, that would be ideal. And if we run out of time, of course, you can take your discussion to Slack. Just a friendly reminder, we have a code of conduct that you clicked and agreed to when you registered for this, and this can be found on the website at the resources. Rubin adheres to the principles of kindness, trust, respect, diversity, and inclusion in order to create a nice, pleasant learning environment that produces rigor and excellence. Any discriminatory behavior against colleagues on the basis of anything, gender identity, race, et cetera, is not going to be tolerated. If you witness any form of bullying or harassment or aggression, please report based on the instructions in the code of conduct. All these talks are being recorded. I've recorded this, starting recording. The videos will be posted the next day. If you see questions in Slack, which are similar to the questions you want to answer, post a thumbs up so you can upvote them, and these will get priority in trying to be answered during the question and answer session. If you want to show your appreciation, you can clap or applaud silently at any time with that sort of indication on Zoom, or at the end of the talks, you can open your mic. As I said, any questions through Slack or Zoom, and of course, you can access the presentation material on the session page. I have control of the slide deck, and so I'm going to advance the slides. And so the speakers just tell me when you want to advance, and we'll do so. Okay, so let's begin. The first talk of the day is by Somayeh Khakpash, which is feature definition and classification of microlensing light curves.
Thank you. Today I want to talk about an idea that we've been working on. I will first give you an introduction. Microlensing is a phenomenon where light coming from a distant star is lensed by a star in the middle, and as a result, we see a magnification in the light curve of the source star, as you see in the left image here. And in the cases where the lens is either stellar binary or a planetary system, the complex features that appear in the light curve do not usually have direct relation to the physical parameters of the binary system. So as you see in the left image, I have a schematic representation of a binary lens microlensing light curve, and you see the features appearing in a light curve. I have marked them with different properties, and what we're saying is that these properties do not have a direct relation to the physical parameters of the system. So the idea is that simple heuristic models can be fitted to the light curves to extract these features and then use these features as classification inputs. And on the right-hand side, you see an example of a heuristic model fitted to a binary lens microlensing light curve to extract these features. Next slide, please. All right, so before we want to use these features as input to machine learning classifiers, we want to evaluate how useful they are. So we do that by different ways, either comparing the estimated parameters to the true parameters, or by looking at the distribution of the features for different classes of light curves. An example of this sort of evaluation is in the image on the right. We have one of these features that we extract from these models, and we look at the distribution of this feature for different classes of light curves. So these features then can be input to machine learning classifiers, and we find that some of these heuristic models can be also useful to extract features that can be used to classify microlensing light curves versus other types of stellar variability. Next slide, please. And so we have tested this method for high cadence light curves that were simulated for Roman Space Telescope. And we trained 4 different machine learning classifiers using these features, and the preliminary results of that seems to be successful. We are interested to test that for lower cadence surveys like the Rubin's microlensing Lightcurves in the future. And since the observing strategy for the Rubin is not yet finalized, we're interested to see which of the observing strategies would yield the most optimum results. On the right-hand side, I have 2 examples of the preliminary results of the classifiers. The left image is the confusion matrix for random forest that we trained using these features to distinguish between single lens and binary lens microlensing Lightcurves. On the right-hand side, you see a confusion matrix for a neural network that we trained to distinguish between stellar binary lens and planetary binary lens Lightcurves. That's all.
Great, thanks. Next up is Natasha Abrams.
Hello.
Talking about hunting gravitational wave black holes with microlensing. Go ahead, sorry.
Hi. So we approached the problem of calculating the microlensing event rate analytically. So we're integrating over the number of lenses passing in front of sources where the sources are in the bulge, and then the lenses are either in the bulge or in the disk, the Milky Way. And so that integral will depend on the spatial velocity and mass distribution of the lenses, where we assume the velocity distribution is the same regardless of the component, i.e. the white dwarfs, black holes, etc. And this ends up with a mass squared dependence in the integral. For the mass distribution, we assumed the main sequence stars followed a Krupa-like mass function, where the more massive main sequence stars all evolved to their later life counterparts. In the image on the right, the light blue evolved to white dwarfs, light green to neutron stars, and gray to the black holes, where we looked at 2 different mass functions, a toy Gaussian model and a similar to the LIGO predicted power law spectrum, where we assume number conservation. Next slide, please. So as you can see, even though both black hole models had the same number of black holes, due to the mass squared dependence in the integral, you end up with this, this shoulder from the most massive black holes in the power law spectrum. And hopefully, in theory, one could then measure this, the number of events as a function of the Einstein crossing time, and hopefully then extract the mass function underlying that, or the black hole mass function. Next slide, please. And so then we looked at a few LSST sample cadences to see which could best be used to observe this shoulder. So we simulated 12,000 Lightcurves with various minimum impact parameters, peak times, and Einstein crossing times. And had 2 different criteria, a trigger criteria with a 10% amplification with at least 2 observations, and a detection criteria with a 10% amplification with at least 4 observations on either side of the peak. And at low Einstein crossing times, we got that the cadence was best in the bulge and the baseline, but at high Einstein crossing times where you would see that shoulder, there was little difference between the cadences, where the only difference was edge effects. So hopefully, regardless of cadence, we would be able to observe the effect of the black hole mass function. Thanks.
Great, thanks. Okay. Next, Niel Brandt is going to talk about the XMM-SERVS project.
Hi, so I'd like to talk about a large X-ray survey project that about 30 of us, mainly people from the AGN science collaboration, have been working on for the past couple years. And this is the XMM-SERVS project, aiming to get high quality X-ray coverage with the XMM-Newton observatory of prime parts of the LSST deep drilling fields. And I want to highlight the work of my graduate student, Quingling Ni, who has been working very hard on this full time for the past long period. So the deep drilling fields have been chosen, of course, to have excellent multi-wavelength coverage generally. And that's what's shown in these little images here relative to the 10 square degree LSST fields. You can see with the various color-coded shapes a lot of the multi-wavelength coverage as labeled. But a clear omission among that was good and uniform X-ray coverage, especially over several square degrees. Cosmos had some, XMM-LSS had some, but it was patchy, and the other fields really didn't have it. And so XMM-Newton can fix this with its large collecting area, its large field of view, its good angular resolution, and its good bandpass, make it a very effective surveying instrument for these types of fields. And this is critically important, the X-ray coverage, because X-rays are essential in providing a ground truth sample of active galaxies, which we can calibrate in the LSST deep drilling fields and then scale up to the full LSST survey. Next slide. So this plot here shows the X-ray coverage that we're getting in as the yellow shapes. So we proposed for an XMM-Newton heritage program. We won in total now about 5 megaseconds of time. We're covering about 4.5 square degrees of XMM-LSS. That's actually done and published. And we currently have data incoming on the wide Chandra Deep Field South region and the Elias S1 region. And we're getting the coverage at about a 50 kilosecond XMM-Newton depth. And among these fields, we expect to have about 11,000 AGNs, as well as many X-ray groups and clusters in the field. And we can, of course, do exciting science immediately, particularly as sort of highlighted in this slide, exploring supermassive black hole growth across the full range of cosmic environments, minimizing cosmic variance, and investigating supermassive black hole galaxy connections. And then, of course, in the future, this has incredible legacy value as LSST and DES deep drilling fields, as moons and PFS spectroscopy fields, as Toltec and ALMA submillimeter fields, as well as multi-object spectrometer reverberation mapping fields. Next slide. And so just very quickly, here are just some of the results. So on the left, I show the sources, the X-ray sources from the XMM-LSS field. We have 5,242 X-ray sources there. We have already successfully found counterparts and either spectroscopic or photometric redshifts for many of those. And those are sort of as labeled with the colors. This is work that's been published, led by Chin-Ting Chen, who worked very hard on this. And then on the right, I show our current data. The data is still incoming a little bit for the Chandra Deep Field South region. And there we have about 3,600 X-ray sources, and you can see the beautiful panoramic XMM coverage going well beyond the original Chandra Deep Field South, which is that little region in the center as labeled. And we also have about 2,000 sources in Elias S1. And again, about 90% of the X-ray sources across all the fields now have reliable multi-wavelength counterparts, and we are looking forward to using these in conjunction with the LSST data. Thanks.
Thanks, Niel. Okay, last one, Dragana Ilic, time-domain mapping of light echoes from AGN core. Dragana, are you here?
I'm here. Do you hear me?
Okay, yes, hear you now. Go ahead.
Yeah. Oh, well, my internet at the university collapsed, so I'm using my phone. So hopefully it will work. So hello, everyone. I'm talking here on behalf of the Serbian AGN team, and I'm going to talk about our time domain investigation of the AGN core, which are usually hidden to direct imaging. So we want to use the light curves, which of course the LSST will provide. And I just want to say, they emphasize that the reverberation mapping, but the time domain analysis of AGN light curves is one of the priorities of the AGN size collaboration, because we want to study both the AGN accretion disk and broadline region through the reverberation mapping. So next slide, please. I want to just present some of the results, basically investigation of our own campaign, which has a set of AGN of different properties and inner structure. For example, one of it is the candidate for a binary AGN. And what is important is that we have 10+ year long light curves. And in our analysis, we have assessed some of the problems which you can reach while having the long-term light curves, especially since LSST will have the light curves of 10 years length. And so, for example, we addressed problems like gaps or non-uniform cadence, and that's why we developed a tool to simulate the light curves, which is based on machine learning, that is the Gaussian processes. And this tool can be used as a complementary tool to any of the LSST infrastructure. Next slide, please. Another thing that I want to present is that from this data set, we constructed a matrix for the cadence estimate necessary for reverberation mapping time lags. And you can see here the proposed matrix, which is based on our own long-term data set. And basically, depending on the accuracy of time lags that you want to achieve, you should have the different basically cadence. On the central slide, central plot, you can see the errors or in time lags with respect to the set cadency in your campaign for different redshifts. And the same thing, similar in the table on the right, is the range of cadences for different properties of light curves if you want to achieve the accuracy of your time lag estimates of 10%. So this is a very simple metric that can be easily incorporated into the LSST infrastructure. So that's it. Thank you.
Great, thanks. Okay, we have time for questions for any of these talks. I'm going to get out of sharing mode so that I can sort of hopefully see your questions a little bit easier. And let's see. Sophie, are there any questions on Slack?
No questions so far in either the chat or on Slack. So speak up, people. If you've got questions, let us know.
Okay, I'm gonna do the chair's prerogative here and ask a question for Somayeh, the first one, and I can actually point to the slide I want to talk about or have a question on. So when you set up this random forest classifier, did you set up any nuisance classes to try and fool your classifier?
Can you repeat your question?
Well, so it looks like you have classes for single and binary lenses here, but did you set up anything where you have like a null result? So you have a class that's essentially a null sort of class.
Well, no, not for this classification, because it depends on the data set that you have, and the data set we had was simulated and was already labeled, so we knew every what are the classes of each of them. But and we didn't try adding a null class, but that would be actually interesting to see if that's what would be the result of that.
Yeah, I mean, so I guess the goal here is then to just study things that have already been identified as possible microlenses.
Well, the ultimate, one of the things that people are really interested in, and we want to test that, is to basically see if we can quickly identify the light curves that are most probably due to planetary systems. So we want to be able to quickly find out which ones are binary lenses versus single lenses, and also find out which ones stellar binary lenses or planetary binary lenses. And we will the hope is that we can get as many possible the planetary system lenses.
Do you need any other information besides the light curve? I mean, would it be helpful to follow this up while it's happening? And would you be able to identify the light curve if you only had, say, half of it?
So, well, it depends on which survey we're looking at. So for the Rubin, yes, definitely we're interested to basically follow them up. And well, that problem is kind of different from what we're working on right now. So we're looking at the full light curves after the survey is done, or most of it is done. But there's also the problem of classifying in real time, and then planning for observations, which is also a really interesting problem people are still working on it. But yes, follow-up observations would definitely help a lot in constraining the parameters and also like covering the light curve in cases of low cadence surveys.
We have a question coming in on Slack as well from Robert. Do you want to unmute and ask your question? Or I can ask.
Yeah, sure. No, I can do it. I can do it live. Hi, Somayeh, I had a question for you on the same slide. So in your confusion matrix, I think my impression is that the numbers, the confidence in the accuracy of the classification are not that great, right? False positives of 10 and even 30% in the neural network case. I was wondering if you have ideas how to improve the accuracy of classification and maybe as the survey continues and goes on year to year, whether this will improve those numbers.
Yeah, so one significant factor I think will significantly improve the results is to expand our data set. So our data set wasn't like so large. Like we had about like 4,000 examples of like microlensing light curves. And I think if we increase the examples, if we increase the have a larger data set, that would definitely help with the accuracy of the results. And also we should definitely work more on like tuning the hyperparameters and also basically finding the value of the features so that so far we've done some preliminary like hyperparameter tuning and then finding values of the parameters, but we need to basically explore that in more details. And because like each of these algorithms are really like, some of them are really sensitive to like the types of features that you input to that algorithm, and that should be investigated in more details.
Thank you.
Okay.
I haven't seen any more questions come up, but I have one. In a sort of, this is for Niel Brandt, in a kind of hand-wavy way, how deep is 50 kiloseconds for somebody who doesn't know what a kilosecond is? And how does that relate to sort of the magnitudes that LSST will see for stuff?
Yeah, so it's challenging, of course, to match the full LSST depths, especially over these types of things. I mean, ideally what you'd like is to have something the depth of the Chandra deep fields, which are million-second Chandra observations over these entire sky regions, but that is just insanely expensive right now. So to give you a sense, though, this is sufficiently sensitive to detect quasars to very high redshifts in the X-ray band, and to detect Seyfert type AGNs out to redshifts of order 1 to 2, depending on obscuration level. Okay, so that's the kinds of luminosities that we're able to detect. In the future, there is a mission, of course, Athena, that the Europeans are aggressively pushing forward. And I have heard in discussions that these LSST deep drilling fields would be prime targets for the Athena surveys program. And that would be, you know, nearly, not entirely, but getting not too far away from Chandra deep field depths over the entire LSST deep drilling field. So we are doing the best we can, you know, while keeping the cost manageable. And you can see from the slide, again, this is a 5 million second XMM investment. So it's a very large investment. We're very grateful to the XMM team and to the whole, you know, ESA for investing in this program. We're doing our best to get the most we can while keeping it not insanely expensive. Is that answering your question in a hand-wavy way? I mean, I'm happy to give you numbers as well.
Yeah, I mean, you can probably guess what I'm interested in, and I think you were heading that way anyway with your answer. We did have one more cam up on Slack from Robert again.
Yeah, it was just a quick question, Dragana, whether the Gaussian process code that you mentioned for time series, whether it's open source and available?
That's a good question, and that's what we are working on it, and we want to develop. It's a sort of still involves a little bit of modeling, and that's why it's not so fast as maybe some other processes that you can involve. So we're working on it to make it faster and to make it available.
Thank you.
That's the plan. That's why we thought of a name.
Very good. Thanks.
Thank you.
Any questions?
I'm not seeing any more questions come up on either chat.
I guess I have a question for Dragana, kind of related to Robert's question, but you kind of you hinted at the fact that this would be useful as a metric, and so there are ongoing discussions now, and in fact tomorrow I guess we'll hear a long discussion about the need for metrics and cadence discussions. So is it possible that this can be implemented into a metric, and so you can actually,
well, that is thank you for the question, because I didn't have time to address this. In principle, this is what we want to achieve because so far this metric is based solely on the physics of the light curves, basically on the physics of the AGN. So it's introducing basically only the intrinsic property of the AGN. And so what we want to do is basically see how can we incorporate this into the sum of the facts that you get, not the facts, the input data that you get from the OPSIM, like the magnitude, the coordinates where you observe and so on, and just to combine those two and basically use it as a quick metric for the test of cadences in terms of AGN light curves. So this is basically the plan. So to introduce, to introduce more like instrumentation data into the metric, not just the properties of the objects itself. So to be more precise.
Yeah. Okay, thanks. Any last questions?
Not that I'm seeing.
Okay, if not, then let's thank our 4 speakers. We're going to have another half-hour session in a few minutes, so we can always come back and get new questions at the end of that session. So let's thank our speakers. And we're going to take a little bit of a pause, and we'll restart up in about 5 minutes. Okay, or 4 minutes.
Session en parallèle. Alors, vraiment, des problèmes techniques, donc il y a du retard. J'étais débronzé. Ouais. Oh. J'ai vraiment pas fini alors ou quoi? Je sais pas, enfin, ouais.
Okay. As per the suggestion by the management, we're going to swap chairs at the break. So Sophie's going to do the honors the second time over.
Can everyone see that? I'm going to use these couple minutes to test. Can anyone hear me or see the slides?
Yeah.
I can hear you and I can see the slides. Yep.
Yes.
Thanks.
I also see some little Zoom chat window on top of some of the slides.
Sophie, you apparently have a version where that's not hidden.
I'll remember that for when I'm Zoom chatting about some sort of dreadfully private matters.
The trick is to run Zoom on your phone.
What I also can't do from in here is really see the time. So are we at about transition time?
Yeah.
We just left our other one and they're showing up here.
You can probably hold one more minute.
Oh, hi, Franz. It's nice to see you in person. I've talked to you so many times on Slack. To wait to the AGN stuff in DC2.
I left a bunch of comments. Sorry.
Okay, shall we start then as the participant number is stabilized? Welcome to the second session about AGN and microlensing. We're sorry that we're going to eat into your break before the session after this one. We have a brief agenda. We're going to give the 4 talks. You know how this works now. 3 minutes each, and then a question and answer session. Please put your questions preferably into the Slack channel so that there can be discussion continuing after the session. Speakers, you know how this works, but I will move your slides for you. You've all heard this before. Please be kind to each other and report anybody being nasty. Again, give questions that you would like to prioritize a thumbs up and show appreciation to the speakers. And we will start with our first person who's going to talk about the feature definition and classification of microlensing light curves, Somayeh Khakpash.
Hi,
Sophie,
everyone.
can you minimize your Zoom window to the side? Yeah, there you go.
Okay. Hi, everyone. So today I want to talk about an idea that we've been working on. So for those of you who don't know, microlensing is a phenomenon where the light coming from a distant star is lensed by a star in the middle, and as a result, we see a magnification in the light curve of the source star, as you can see in the left image here. And the case where the lens is a binary lens, either a stellar binary lens or a planetary binary lens, the light curve has complex features that do not have direct relation to the physical parameters of the system. So in the image on the left, I have a schematic representation of a binary lens microlensing light curve. You see some features in the light curve, and I have marked them with different properties. And what I say is that these properties are not directly connected to the physical parameters of the system. And the idea is to fit the light curves with simple heuristic models to extract these features and then use them to classify them. On the right-hand side, we see an example of a heuristic model that is fitted to a binary lens light curve to extract some features. Next slide, please. In order to use these features as input to machine learning classifiers, we first evaluate them, and we do that either by comparing them to comparing the estimated parameters to the true parameters, or by looking at the distribution of the parameters for different classes of light curves. On the right-hand side, you see an example of one of these features that we extract from the light curve, and then we look at the distribution of that feature for different classes of light curves to see if this is a useful feature to use for classification. And so the idea is to input these features into machine learning classifiers, and we show that some of these algorithms are also useful for detecting microlensing light curve among other type of stellar variability. Next slide, please. And we have tested this method on high cadence light curves that were simulated for Rubin Space Telescope. And we trained 4 different machine learning classifiers using the features. And the preliminary results of that shows that this works successfully. And the idea is that to test these models for lower cadence surveys like Rubin microlensing Lightcurves, and then for the Rubin, since the observing strategy is not yet finalized, we're interested to see which of the observing strategies would give us the best results. And on the right hand side, you see two examples of two of the classifiers that we trained using the features. And the left-hand side is a random forest classifier that we use to distinguish between single lens and binary lens Lightcurves. And on the right-hand side, you see a neural network that we train to classify stellar binary lens and planetary binary lens Lightcurves. And that's all.
Okay, we can move on to the next person. We have Natasha Abrams talking about hunting gravitational wave black holes with microlensing.
Hi. So we approach the problem of calculating the microlensing event rate analytically. So that involves integrating over the lenses passing in front of the sources, where the sources are in the bulge, and the lenses are in the bulge or the disk of the Milky Way. So that ends up with an integral depending on the spatial, velocity, and mass distribution of the lenses, where we assume the velocity distribution to be the same regardless of the component, i.e. white dwarf, black hole, etc. And that ends up with the mass squared dependence in the integral. For the mass distribution, we assume that for the main sequence stars, they followed a Krupa-like mass function, and that all high mass main sequence stars evolved into their later life counterparts. So the light blue to the white dwarfs, light green to the neutron stars, and the gray to the black holes, where we assume number conservation between each of those. We looked at two different black hole models, a toy Gaussian model, you see in the dashed line, and the LIGO-like power spectrum shaded in. Next slide, please. So even though the two black hole models had the same number of black holes, because of the mass squared dependence in the integral, you end up with the big shoulder from the power law mass function from those high mass black holes. And so in theory, if we were to measure the total number of events as a function of the Einstein crossing time, then we could extract the black hole mass function from that curve. Next slide, please. So we looked at 3 different LSST cadences to see which would be best to observe that shoulder. So we simulated 12,000 Lightcurves with various minimum impact parameters, peak times, and Einstein crossing times, and had 2 criteria: a trigger criteria with a 10% amplification with at least 2 observations, and a detection criteria with a 10% amplification with at least 4 observations on either side of the peak. And at low Einstein crossing times, looked like the alt-like cadence of the best out of the 3, then the bulge re-optimized cadence, and then the baseline. Though at high Einstein crossing times, since the duration was so large for those events, there was little difference between them besides edge effects. So hopefully, regardless of cadence, we would be able to look at that shoulder or lack thereof. Thank you.
Okay. Next, we have William Brandt talking about XMM-SERVS.
Hi, so I'd like to talk about a large X-ray surveys project that about 30 of us, mainly from the AGN science collaboration, have been working on for the past couple years. And this is the XMM-SERVS project, which is getting high quality X-ray coverage with the XMM-Newton Observatory of prime parts of the LSST deep drilling fields. In this, I want to highlight the work of my PhD student, Qingling Ni, who has been working very hard on this full time for an extended period now. So the deep drilling fields were chosen of course, to have excellent multi-wavelength coverage generally, and you can see that from these little images of the deep drilling fields that I have here, where with the various colored shapes I've superimposed on top of them, as well as the shading for the Spitzer coverage, you can see all the multi-wavelength data. But a clear omission from all this multi-wavelength coverage was good and uniform X-ray coverage over square degree scales. And XMM-Newton is able to provide that owing to its large collecting area, its excellent field of view, its good imaging, and its broad bandpass. And for AGN science, X-rays can play a critical role in that they can provide us with a ground truth sample of active galaxies, relatively unaffected by obscuration, for example, that will let us calibrate LSST, then ultimately scale up what we've learned to the full LSST footprint. Next slide, please. So this is what we're doing. So we have now won a 5 million second heritage program with XMM-Newton. And we are getting coverage of the yellow labeled sky regions here. The XMM-LSS region, we actually have already obtained and published 4.5 square degrees of sensitive X-ray coverage there. And then we are presently just finalizing the observations. We're getting the final X-ray data sets right now from XMM on a wide field region about 4.1 square degrees around the Chandra Deep Field South, as well as a 3 square degree region in the Elias S1 sky region. And we are going for about a 50 kilosecond X-ray depth. So this is sort of a moderate depth X-ray survey. And at this depth, with these solid angles, we expect to generate about 11,000 AGNs, as well as many X-ray groups and clusters. And of course, we can use these immediately to do a lot of exciting science, to explore supermassive black hole growth across the full range of cosmic environments, to look at connections between supermassive black holes and galaxies. And then, of course, in the longer term, these data will have incredible legacy value as, of course, LSST and DES deep drilling fields, as well as moons and PFS fields for massive spectroscopy, for Toltec and ALMA submillimeter fields, as well as fields for multi-object spectrometer reverberation mapping. Next slide, please. And so here are just two of the results. So on the left there, I am showing the results from the XMM-LSS region. I'm just showing all the X-ray sources that we've generated in this field as the dots. And the ones colored in blue are the ones where we've managed to find reliable multi-wavelength counterparts already. And then the other sources are in red. We have, again, about 5,200 sources in XMM-LSS. And this, again, is published in a paper by Chen-Ting Chen et al. And then on the right, I'm showing some of the very recent data we've obtained from the Chandra Deep Field South region, where now we have about 3,600 X-ray sources there. And you can see the beautiful panoramic XMM-Newton X-ray coverage around the Chandra Deep Field South. Whereas previously in this sky region, all we had were these little regions in the middle labeled in blue as the CDFS and the ECDFS. Now we have much wider field X-ray coverage that's much better matched to what LSST will be giving. We also have about 2,000 sources now in Elias S1, and we have about 90% of the X-ray sources already having reliable multi-wavelength counterparts. We're working to characterize those so that they can be used, as soon as LSST switches on, they can be used very effectively to get on exciting science. Thanks.
Okay, and our next talk from Dragana Ilic, time domain mapping of light echoes from AGN core.
Thank you, Sophie. I'm Dragana Ilic from University of Belgrade, speaking on behalf of the Serbian AGN team. And I want to say something about our time domain studies of the core of active galaxies, which is usually hidden to direct imaging. And we want to use time domain analysis, and this is the reverberation mapping. And I want to emphasize that the reverberation mapping of the accretion disk and broadband region in active galaxies is one of the priorities of the LSST AGN science collaboration. So here are some of the results from our own long-term monitoring. Next slide, please. So our campaign contains a set of active galaxies with different properties in the sense that they have a different inner structure and a different variability type. And another important feature of our campaign is that it is 10+ year long. In the sense, this is important for the LSST because the LSST will also produce the long-term light curves. So in our analysis, we wanted to address some of the problems which you can have with such a long light curves, and that is how to address gaps or non-uniform cadence, and a tool for modeling of light curves using the machine learning, that is the Gaussian processes, and you can see on the right simulated light curves. And we developed a tool which can be used as a complementary tool in the LSST infrastructure. Next slide, please. Another thing that we developed from our data set is the metrics for estimates of the cadence needed for accurate estimate of the regression mapping time lags. And our metrics is based on our decadal long-term light curves, so basically on the real light curves. And you can see the metrics, proposed metrics here. And what it's shown is that depending on what accuracy of time lags you want to achieve, you need a different cadence. And this is shown in the middle plot, where it is a plot of the uncertainty in time lags versus the cadence of your monitoring campaign for different redshifts. And also the table is showing something similar. And this is the range of cadences based on the proposed metrics for different properties of light curves, that is for different type of AGN and different redshifts. And this can be easily, hopefully, incorporated into the LSST infrastructure to test the required cadences for time lags estimates. So thank you.
Thank you. So I guess now we are going to go to questions. I am going to stop sharing so that we can see people's faces.
So no questions in chat at the moment. Let's see, I guess I'll pose a question for Natasha, I think. So for the model of lensed objects or objects that are doing the lensing, I mean, I guess in some cases there's a huge range, right? I mean, for instance, the number of stellar mass black holes or neutron stars. How did you assume, what went into that assumption for the bulge?
Or you mean like, why'd we choose the mass distributions we did, or?
Well, the mass and the number density.
So the number
density, right?
So the number was just from number conservation from the number conservation from the high mass main sequence stars. For the number density, we used the Bacall et al. For the model of the bulge and the excuse me, Kent model for the disk. So the someone else in my lab was working on ogle data, and she had picked those since they best fit the ogle data.
Okay. And I guess there should be a substantial variation across the bulge, right? I mean, if you look towards the center, it's got a much higher mass density than offset. Did you investigate that at all, or is that relevant to the cadence?
For the cadence, we just assumed that we would be calculating the same number. We just looked at the most dense part and assumed that we'd be seeing the same. There would be the same number of microlensing events happening, and we just would care about which was how many times it was being visited, right? So I guess yeah, we took the most dense part of the bulge. We just looked at the fields in the most dense part of the bulge in the middle.
Okay. Chris, you have your hand up.
Yes.
Yeah.
I had a quick question for Dragana. So this is a very basic question because I'm not an expert. This is very interesting. So when you're looking at the reflection, the time delayed reflection of the light from some other cloud or some other place, is that primarily telling you about time structure that you otherwise aren't able to image because of things around the core? Or is it more that you could image them around the core and it's just a way to fill in time areas that you weren't looking at before? I sort of missed the basic point.
I'm sorry, didn't have time to introduce the topic. So the point is that the AGN core is so small that you cannot resolve with direct imaging. So basically what we did so far is that we only resolve it with the Event Horizon Telescope and with the gravity instrument at VLT. And that was done also for 2 sources or 3 sources. So that's why we need to employ this time domain analysis, which will basically give you the size and of different structures within the core. So basically, well, the accretion disk and the broadline region. So we have been studying mostly the properties of the broadline region, and when you can do this sort of regression mapping, you can get the whole, not just the structure, the size, but also the kinematics and the geometry of the broadline region. And this is
So by seeing sort of the amount of time it takes to cross over,
yes,
doing the forward transform
yes,
stuff,
that's for the broadline region, right? Yes.
Oh, thank you very much. That's really interesting.
Thank you.
Other questions? A question for Niel. So when do you expect the Kinling's paper to come out on the CDFS?
Yeah, right. So we are just presently getting the final observations. We've actually covered the entire footprint once, but as you know, XMM-Newton suffers from flaring from time to time. So we have these makeup observations, which are already built into the program. We're getting those done now. In fact, I just got emails this morning that some more have been scheduled for late August. So as soon as we have those data on the ground, we have a full data set. But we haven't been, of course, waiting for that. We actually have a draft paper already. If you can't wait, Franz, because you're one of the collaborators, I will send you the draft and you can give us some feedback. You know, in about 30 seconds, I can provide it to you. But we are making rapid advances on it.
Okay, cool.
So it's a, you know, it's not a highly polished draft yet, but it shows essentially what you're going to have. And so we have it there. We are certainly committed to getting these data processed promptly and publicly released the same way we did for Chen et al. And so, you know, the aim is to make all those X-ray sources publicly available so people can go to town on them across the electromagnetic spectrum or with spectrographs or whatever. So we'll have the best possible AGN ground truth data set, as well characterized as possible, locked down by the time LSST switches on. That's the aim. And so we're going as fast as we can. If XMM observes them faster, we'll have them out faster. But, you know, to get that much time across those fields, and especially if you want to have makeups so you don't have holes in the field, it just takes a while. You know, they've actually done it faster than they have to. It was a 3-year program that they approved. And they're getting it done in 2 years or 2.5 years or something like that. So we're actually doing rather well. Yeah.
Any other questions for any of the speakers?
Can I ask a question for Niel?
Sure.
Sure.
So on the X-ray data, just in terms of the depth, you know, for the deep drilling fields, there's presumably some number of AGNs which you expect to be identifiable in LSST.
Yeah.
So what fraction of that number are you expecting to be detected in the X-ray data, and what fraction is going to be below the detection limit from XMM-Newton?
Right. Okay. So a bunch of things there. First of all, you will detect, you know, some optical light from huge numbers of AGN. For example, in the Chandra deep fields,
sure, yeah,
there we get to like 23,000 AGNs per square degree, something like that. Whereas here we're getting to about 1,000 AGNs per square degree. So we're doing sort of 1/20th the number density on the sky of the Chandra deep fields. So LSST, of course, will detect some optical light from all of those Chandra deep field south AGNs, just from the fact that they have host galaxies, if nothing else. But whether LSST will be able to show that they're AGNs or not is the million-dollar question. LSST can go after that, of course, with colors for the bright ones, with variability, with lack of proper motion, and so on. And then when you have additional multi-wavelength data, you can bring that all to bear. But right now, the best forecasts, I mean, I will be happy if in the deep drilling fields we get up to, I don't know, I'd be happy if we got to a few thousand AGNs per square degree. And so, you know, the X-ray data will be giving you, well, we'll have to see how we do, but, you know, a substantial fraction, but probably not all of the AGNs that you'd be able to find with LSST. And that, I think we'll learn a lot from exactly doing those types of analyses. How well do you select AGNs in different ways? People are making progress on that right now. For example, if you look at the if you look at the deepest available optical AGN variability selection surveys, Dimitra DeCicco in Franz's group, in fact, has been leading some of that work. I believe they're getting to something like, what is it, Franz? 200 to 500 AGNs per square degree, something like that. Okay, LSST should be able to do better because it's deeper, it's multi-band, you have higher quality imaging, and so on. But you know, we'll have to see how well we can do. I mean, I think LSST alone probably will be pretty well matched in depth to this. That's one reason why we did the X-ray data as deep as we did. But when you start to bring to bear LSST plus Euclid plus, you know, all the radio data and all the other multi-wavelength data, then I think the numbers will start going up, you know, to a few thousand per square degree, something like that. Is that helpful, Matt? Am I addressing your question, or do you have a follow-up? It was a multi-part question.
Yeah, I was specifically interested in the identifiable AGN as opposed to just the detectable ones. But the identifiable, combined with the infrared, it makes a big difference for the infrared as well. Absolutely, yeah, the infrared is going to be essential. And thankfully, I didn't mention this here today, but of course, Mark Lacey has conducted the original SERVS program. That's what that SERVS stands for. It's the Spitzer Extragalactic Representative Volume Survey. And then Mark has now actually covered the full deep drilling field footprints for XMM-LSS, Chandra Deep Field South, and Elias S1. And so, I will tell you, just a few days ago, Mark Lacey submitted his deep drill paper on the Spitzer data. And so there'll be a great Spitzer data set out there. And, you know, we're committed to getting the X-ray data set out there. And so we really hope to hit the deep drilling fields hard and fast as soon as LSST switches on.
One last question from Lorena Hernandez in chat. Lorena, do you want to ask it, or do you want me to answer it for you?
Hello?
Lorena Hernandez, not Martinez. Okay, I'll ask. So is XMM thinking about doing a follow-up of AGN, or just to get the detections of as many sources as possible?
You're asking about in the program that we're currently doing?
I think so.
Okay,
or just follow-up of AGN in general as a function of LSST detection.
Well, oh, right. Okay. So, well, I'm sure when people find interesting AGNs in the LSST, you know, 18,000 square degree footprint, they find some new AGN that's varying in a crazy way or has remarkable colors or whatever. I'm sure that individual investigators, members of the AGN science collaboration, for example, will go in, find those interesting AGNs and propose them to XMM-Newton for follow-up in the X-ray. That's the same game that many of us have been playing for the past 2 decades. And so I surely expect that will happen, but I'm not aware of any large-scale coordinated program where somehow ESA has committed to working with LSST to do some highly organized program. I think it's going to be up to individual investigators and their initiatives to go and do that. But I surely think that'll get done by many individual people. Certainly people in the AGN science collaboration have interest in doing those kinds of things.
Great. We got one more question. Mark, you have a quick question?
Yes, this is a question for Natasha. I would like to know if you studied the the degradation of the detection efficiency when the sampling is degrading. I mean, what would be the worst gap load? Is it months? I think it's probably months, not years. That would allow you not to degrade too much the efficiency of microlensing detection for the 10 solar mass objects typically. Did you do such a study?
I guess not particularly for the 10 solar mass objects, though. I mean, they're all going to have on the order of month gaps because like the bulge isn't visible from the southern hemisphere for months at a time. But that would be interesting to look into.
Yeah, because there is some risks to have a few months gaps in the light curves. That's why I am asking this question.
Yeah, of course.
So you have to keep this in mind. I think up to 6 months should be okay for the longest events, but as long as you are looking for events that are shorter than typically 1 year, your efficiency should really degrade seriously.
Yeah, I'm sure that, yeah, like as you saw from the plots, like even with like, I mean, of course, when there are objects on the order of like a few days or a few months, even if you skip a few months, then of course you miss them. And yeah, it just depends on the duration of the event.
Okay.
So I don't know the exact figure, but yeah.
Okay, great. We want to thank the speakers again. And so we're going to end our session now. Thanks for bearing with us through the technical troubles. Hopefully they'll sort that out on the higher end. And the next session will begin in about 15 minutes, okay? So thanks everyone.